Okay, well, welcome to this last day of this GCT series. Today, it's my pleasure to invite Markus Bläser from Saarland University. In fact, Markus was the first one to reply when we asked people if they want to come and actually have it on site. He agreed immediately. Unfortunately, we couldn't have it on site. Yeah. So Markus will be telling us about irreversibility of tensors of minimal border rank and barriers for fast matrix multiplication. Yeah.
Okay, so thank you. And I would love to be now in Chennai, right? Because I'm really, I guess, as most of you, fed up of these online. Well, it's of course great you can join some talk somewhere, but somehow nobody accepts that you are on a conference for a week while you're still being at home. So that's it's always very difficult. Yeah. So today I will speak about irreversibility of tensors of minimal border rank and some barriers for fast matrix multiplication. So most of this is based on several joint works with Vladimir Lishikov, which I forgot to write on the title page. With Vladimir Lishikov, who's still in Copenhagen. And so this talk will essentially have two parts. So these are here now 4 parts, but essentially there will be 2 parts. So talk a little bit about the classical matrix multiplication algorithms, the fast matrix multiplication algorithms. How does the theory work? So maybe some of you, or maybe many of you, know already a little bit about this. So if I'm too slow there, you can simply speed me up, and I go on a little bit faster. And then I will tell you how this relates, or what are barrier results from fast matrix multiplication. And then I will talk about how this relates to methods that we use in GCT, so orbit closures, null cones, moment polytopes, and so on. Okay, and so let's start with something very simple that you all know, right? This is matrix multiplication. So we have 2 matrices, X and Y, and we want to multiply them and think of the X and Y being variables. So we have n squared many bilinear forms that ij, and they are given by these well-known formulas, and we work in the well-known algebraic model. So we have additions, multiplications, and scalar multiplications. And of course, now this looks so natural. You can ask yourself, right, how can I do this faster? Yeah, but astonishingly, and this is one of the milestones in algebraic algorithms and algebraic complexity theory, Strassen saw this way of multiplying 2x2 matrices faster, right? So I've written here the algorithm on this slide. You have seen them, but essentially you can already forget about it, right? So it's not so important how this, of course, for the algorithm itself, it's important how it works, but for the purpose of this talk, it's not so important what the 7 products are. The only important thing is that these products, they are bilinear, right? So we have the X variables here, and we have Y variables there. So these are bilinear products, and all of these products are of this flavor. Yeah. Before this, one had already there was an algorithm by Winograd who could also do it a little bit faster, but the algorithm was not bilinear, and you could not use it recursively. Right? So therefore you didn't get any improvement in your exponent by this Winograd twist. Okay, and of course now you can ask yourself, what I have 7 multiplications and 18 additions now if you counted properly on the previous slide, and the trivial algorithm, it has alt multiplications but far less additions. Yeah? And the crucial observation that was made by Strassen is that this algorithm works over any ring, right? So we didn't use the commutativity of these variables because these products, they were bilinear, and therefore we can essentially recurse, right? So that's what you find in many of the undergraduate textbooks on algorithms. This is one of the astonishing recursions. So you take a big matrix, you divide it into 2x2 block matrices, and then you apply Strassen algorithm to this block matrices, and this block matrices you multiply this recursively, and then you get that the cost for multiplying n by n matrices, this is just 7 times the cost of multiplying n over 2 matrices plus the additions now. Yeah, and now for these matrices, right, additions, they're much more cheaper than than multiplications for matrices, because right at the moment, back 1969, we only know how to do this in n cubed, and not better, and therefore you get this improvement. And this is the famous result by Strassen, that you can multiply n by n matrices roughly in order of n to the 2.8 one many operations. Okay, and of course that's great. So we can phrase this a little bit more general, and in a more general flavor, we can phrase this as a tensor rank problem. So in general, we have, say, any bilinear forms B1 to Bn. In our case, this would be the entries of the two matrices. And we have the x variables, and we have some y variables, which would be the entries of the one matrix and the entries of the other matrix. Then we take some bookkeeping variable zij, and then you can write, you get a trilinear form here out of these bilinear forms. And you know, because this is trilinear, you know that you can expand this as the sum here. Then we have these structural constants here in the front, and they form a three-dimensional array of numbers. And you can think of this as being a tensor in this corresponding space here in coordinates. And this is, we call it a tensor corresponding to these bilinear forms B1 to Bn. Okay, and then we have the so-called rank 1 tensors, and these are the tensors that we essentially can write as one tensor product. And if you want to think in three-dimensional arrays, these are just the tensors that you can write as ui, vj, wk, right? So you have three vectors, and you essentially form all. This is generalized as a rank 1 matrix. In a rank 1 matrix, you just would have 2 coordinates, and now we have 3. And then, like for matrices, where the rank of a matrix is the smallest number of rank 1 matrices that you need to get this, that you need to add up to get this matrix, you can define the rank of a tensor in the very same way. The only unfortunate difference that we have is that for a matrix, you have many equivalent definitions for the rank, right? It's, you can have the row rank, the column rank, you can have the smallest, the largest non-vanishing minor. But for tensors, in some cases, it's not clear how to generalize these notions, but they make a difference here. And in particular, computing the tensor rank is a hard problem. It's NP hard. And more general, it's complete for the corresponding existential theory over the underlying field. This is a hard problem, and which makes, of course, the problem hard, but it also makes it interesting. Good. And then, like for matrices, we need 2 operations. So when we have two tensors, we can form their direct sum here. And this is just, by the way, if you would have matrices, then you would just do a block matrix where the 2 blocks are on the diagonal. And we do the same now in 3 dimensions, right? So we take the 2 tensors here, and we put them into a big cube, and they just meet here at the corner. And then also we have the tensor product, and this also generalizes the tensor product of the Kronecker product of matrices. So it's would be more precise to talk here about a Kronecker tensor product, but I will always call it simply tensor product here. And this is essentially, you take one tensor and you take the other tensor, and every position of this one tensor, you put in the small tensor, the other tensor, and you multiply it with the corresponding constant that's standing in this tensor here. For matrices, here the rank would be additive and multiplicative, but for the tensor rank, this is simply just subadditive and submultiplicative. So this again, one reason what makes this problem difficult, but also interesting, because in particular the submultiplicativity here, this makes without it, if it would be multiplicative, then we would not have a fast matrix multiplication algorithm. We would have some fast matrix multiplication algorithms, but not as fast as we know them. Okay, good. And yeah. In particular, you can also look at this matrix multiplication tensor, right? So this is here's the example for the 2 by 2 matrix multiplication. This is essentially color coded, right? So this is a three-dimensional box, and so this is one dimension, this is the other dimension, and the third dimension is given by the colors, right? So this would be go into the screen, and the layers, they're simply they're coded by colors, right? So the blue ones, these are the ones that correspond to Z11, and so on. And it works here because they're in every position, there's only one entry in every layer. Therefore, you can write it like this. You can simply check, right? This simply gives matrix multiplication. Yeah? Because here Z11, these are simply the coefficients. And when I have drawn nothing, then there's simply a 0. Right? And then Z11 was X11 times Y11. And here it is X12 times, and the one is here, times Y21. Yeah? So this is, it works. And in general, you have this formula here for the tensor of the matrix multiplication. And essentially you can think of this, you have an identity matrix of the corresponding size, and you shift it around, right? So you have the identity matrix 4 times, and it's always shifted in blocks, and this gives you the layers of the corresponding tensor. And then matrix multiplication shares some very nice properties. So the nice property is that when you take the tensor product of two, this here is now a matrix multiplication tensor, right? So whenever I write this here, this is the tensor which corresponds to multiplying k by m matrices with m by n matrices, but this is just notation. It's not so important. And the nicest thing is when I take the Kronecker tensor product of two matrix multiplication tensor, I get a larger matrix multiplication tensor. And this is exactly this recursion that happens in Strassen's algorithm or in any other algorithm. Yeah? You take your big matrix product, you cut it into block matrices, and you multiply the blocks recursively. And this is exactly what is happening here. So this tensor product is essentially just doing it in blocks and do the small multiplications again. So this is the block matrix multiplication. This is essentially the multiplication of the blocks, or vice versa. So tensor product corresponds to this recursion. And the other nice thing is that, which essentially follows from this formula very easily, it doesn't matter as long as the 3 numbers here are the same. It doesn't matter how you permute them. So whether you multiply a k by m with an m by n matrix, or an n by k with a k by m matrix, the rank is always the same. It's also a very nice property, which follows almost immediately out of this view here. But if you want to do this, if you want to take one algorithm and you want to build it into another one, it's a lot of work. There's a famous there's a paper by Hopcroft and Luzinski where for pages they're doing all these calculations explicitly, which because this tensor notion was not known at this time. It was just the early 70s, right after Strassen's paper, and there they calculate everything by hand, and it's pages of calculations. And essentially, if you have this tensor view, it comes out immediately. Okay, so this is the setup, and now we have seen Strassen's algorithm, and you can ask, what does this mean in terms of tensors, right? So, and as I told you before, tensor product, this means recursion. This essentially means if you apply Strassen's algorithm s times, then you take the s-fold tensor product of the 2 by 2 matrix multiplication tensor with itself. And this is then essentially 2 to the s. This is a matrix multiplication of size 2 to the s by 2 to the s times 2 to the s. And what you also know that the rank is submultiplicative. The overall cost will be simply 7 to the s. Then we define the exponent of matrix multiplication. This is simply the infimum over all tau that you can do such that the rank of matrix multiplication is bounded by all n to the tau. And by Strassen, it follows that this omega is bounded by 2.81. Of course, you only get it here for powers of 2, but you can always fill in zeros and then bring it down to n. And this does not work for 2 by 2 matrix multiplication. This essentially works for any starting algorithm, right? So this will be the crucial concept. We always have some starting algorithm in this talk. For Strassen, it was simply this 2 by 2 matrix multiplication algorithm, but it could be an arbitrary k by m with m by n matrix multiplication algorithm, which has some cost. And then in the very same way, like the Strassen did, by doing this recursive tensor power and maybe symmetrize this, right? Because the k and m and n, they might be they might have different sizes. So if you just tensor up, yeah, you will also get something which is not square, but we want to have something which is square here. But if you simply take this tensor product here, where I cyclically shift everything, then this is everything here will be KMN. So this is then again symmetrized. And I have a square matrix multiplication. And the cost will be R cubed. And in this way, I can, even though I start with something which is rectangular, by symmetrizing, I can bring myself always in the situation of Strassen. And then by the very same analysis, just with the symmetrization step sneaked in, which is essentially this 3 here, you get a result, but it's the same analysis for Strassen algorithm. You always get an upper bound of omega, which is given simply by 3 times the logarithm of R divided by the logarithm of KMN. And of course, when you see this, now you can of course ask yourself, are there other Strassen starting algorithms as Strassen algorithm? So is this the best starting algorithm? And that's what people tried. And of course, the first thing that you can ask yourself is, can I multiply 2 by 2 matrices, maybe 6 multiplications, right? This would be the easiest, right? But unfortunately, that's not true. So you need at least 7 multiplications. And then you can ask yourself in the next step, maybe I can take 3 by 3 matrix multiplication. But this is already really hard to compute the rank here. So the best lower bound that we know is 19. The best upper bound would be 23. But we need 21 for an improvement over Strassen's algorithm, not for the current bound. And so therefore it took a very long time, right? So for 10 years, there was no improvement after Strassen algorithm. And then essentially Pan came up with an algorithm how to multiply 70 by 70 matrices with, let me read it, 143,640 multiplications. And if you do the math, if you just plug it into this lemma here, you get the upper bound of omega is 2.79. Okay, so that's great. But there's a structured way of coming up with this algorithm. It's not that he simply starts with this, but he has a structured way how to come up with this algorithm. But it's Strassen's algorithm, by the way, it's used in practice, but this algorithm, so at least I'm not aware of this, because you also get some problems with the memory management, right? Because you have to compute 143, you have to compute this many intermediate products, and you have to store them somewhere, right? So this, and it also depends a little bit on your architecture, but in most architectures, this will mess everything up. And it took a very long time to come up with improvements that might be practical. So the best that I'm aware of is a result by Smirnov, who's able to multiply 3 by 3 with 3 by 6 matrices with 40 multiplications. And if you plug this into a bound, we get roughly the same upper bound as Pan. I'm always suppressing further digits. Right? None of these numbers here is a rational number. They all have lots of digits. Okay, good. So that does not work. Okay, so Pan worked for a little bit, but right after Pan, some exciting development took place, and this was an exciting 10 years for fast matrix multiplication. And the first observation, and this was essentially what is this conference is about, is that border rank might help. So here's a very simple example. I think I don't need to go into the details. So if you have the bilinear map with polynomial multiplication mod x squared, so you want to compute these two bilinear forms here, which have this structural tensor. So you have to stack them on top of each other, right? So this is the top and this is maybe the bottom. And then it's rather easy to prove that the rank of this this tensor here is 3. You can't do better than the trivial algorithm. You have 3 multiplications here, and you simply do them, and that's the best you can do. but you can approximate this by rank 2 tensors. So you have some epsilon, and you can either think of a small we are over the reals or the complex, maybe better the complex numbers. And you think of a small number, but you can also think of epsilon being indeterminate, so that we do the algebraic way of approximation. You can approximate this tensor by these rank 2 tensors here. You simply check this, and there's this epsilon. When epsilon goes to 0, it converges to this tensor here. So approximation can help. At least we all know that. But the funny thing is that, and this is the result by Bini, Capovani, Lotti, and Romani, or one of them, is that you can get rid of this approximation without losing anything, right? So often in GCT we have this problem where we want to understand the border, and we don't know what's in the border and how complicated the border can be. So the concrete border here I also don't understand, right? So I don't understand the border of all rank 24, 27 tensors or whatever. But as asymptotically, I can understand the border. I don't understand it, but I can control it in such a way that I can still get good upper bounds for matrix multiplication. That's the crucial part. And what I proved is this is now the border rank, and the border rank is essentially this approximation. I have written here the algebraic way, and this is what I will mainly use in this talk, but it really doesn't matter. It's equivalent here. So you know your rank 1 tensors, they are now polynomials in epsilon, and then the question is, can I write T as a sum of these rank 1 tensors, which have polynomial entries, and then essentially have the epsilon to the h here, because I'm using polynomials and not rational functions. But if you divide by epsilon to the h here, you get essentially that you approximate T in the limit with this computation. And this h is also called the order of approximation here, and then the border rank is simply the minimum overall h. And this is exactly the same. And now here I have the border rank, but the upper bound that you get is exactly the same as for rank, right? This is somewhere here. This is exactly the bound for rank is the same as the bound for border rank. And a crucial way to see this essentially is that you can get rid of the approximation by interpolation. Because when you perform tensor product, if you perform something like this, then the dimension multiplies. But this approximation order, this only adds. This adds up. And this is the crucial part why you can get rid of this. And of course, the omega is defined as an infimum, right? So we don't care for the finer factors. Okay, and that's cool. And of course, you need, of course, now a new starting tensor, and this is what Bini, Capovani, and Lotti found, and Romani found. Namely, when you have the 2 by 2 with 2 by 3 matrices, you can approximately multiply them with 10 multiplications. The rank is essentially, that's also known. This is 11. So it's really an improvement here. So this is 11 is essentially you do a one Strassen multiplication, which would be 7, and for the third row here, or the third column, you essentially just do trivial matrix vector multiplication, which gives another 4. So therefore you got 11 here. Okay, and as I said, we were talking only about starting tensors. And the next observation was somehow made by Schönhage, or the next result is by Schönhage, who proved what is now called the tau theorem. And he started not with a matrix multiplication tensor, right? So here we still start with a matrix multiplication tensor, but Schönhage starts with a direct sum of 2 matrix multiplication tensors, right? So we have 1 matrix multiplication tensor here, and we have 1 matrix multiplication tensor there. And he can bound the border rank by k times n plus 1. And that's already very efficient if you think about it. So this is a k by 1 with a 1 by n matrix multiplication. and you can prove what you have. Essentially, you have k times n many entries, and they are independent. Yeah, so you can't do better than that, right? So this is already what you need for this here. Yeah, and you get this big scalar product. You get it approximately. You get it with one extra multiplication, right? So this is super. This is really a big. That's a great deal, right? It's essentially buy one, buy two, and you get one for free or almost for free. And this is essentially what this business nowadays is about. Yeah? You need to find something which is very efficient, where you have very efficient computation, and then you need an efficient way to turn this into a matrix multiplication. Because this is, of course, now a matrix multiplication. These are now two matrix multiplication in parallel. Yeah? The question is how can this help? And this is what then Schönhage, this is essentially the main thing what Schönhage did. Yeah, he found a way to turn this thinking, which is not a matrix multiplication, which are two independent matrix multiplication, into an efficient algorithm which could multiply ordinary matrices. And essentially, the result says this is Tau theorem, that whenever you have an upper bound on such a direct sum of matrices, of matrix multiplication, then you get an upper bound for the exponent omega, which is 3 tau, and tau is defined by this equation. And that's again, if you just have here one, or if p equals 1, you have only one product, then you exactly recover this result here. Yeah? So this is no. Yeah. Then you exactly recover this result here. There's the 3 missing here, but we have the 3 essentially here. It's the same calculation, we just didn't symmetrize here. Yeah. But this is again the same result, but it's more general. Yeah. And this is this is super efficient here, and you got a very good, this was really a leap, right? So you jump down from something like 2.8 to 2.55. You get this upper bound when you plug in this example here with the right parameters k and n. I think it's 3 and 4 into this tau theorem. Okay. Yeah. And then, everything things get more and more crazy. Right? Then the next thing is what is called Strassen's laser method, and he finds an even more efficient algorithm for, which is now not even a sum of matrix multiplication. So you have here an identity matrix, and you have there an identity matrix, and so an identity matrix is essentially a scalar product, as we have seen in the beginning, where the matrix multiplication tensor, this is just these shifted identity matrices, and every identity matrix corresponds to one entry in the result, and that's essentially a scalar product. The point is that these two things here, they have the wrong directions. If this identity matrix, which goes in this direction, if it would have been turned like this, then this would be 1 by 2 by a Q matrix multiplication. But unfortunately, it's in the wrong direction. So it's not a matrix multiplication tensor, but it has a very efficient computation. So Strassen essentially shows that you can write the Strassen tensor here. So this is here this picture written out. This has the border rank is q plus 1. So you just have to spend more. This has a dimension q plus 1, and its dimension here is q. So you can't do better. This is already matches the maximum dimension of this tensor here. So this is in some sense optimal. You can't go below this. And this is what we call a tensor of minimal rank, when you can't go, when you're ready, the border rank is the same as the dimension of this tensor. But unfortunately, it's not a matrix multiplication tensor at all, and this is where now where we now need to work. And before we do that, maybe I should simply briefly introduce restrictions. And essentially, when I have two tensors, T prime is a restriction of T, if there are linear maps such that when I from the ambient spaces here from V1 to V1 prime and V2 to V2 prime, such that when I apply the tensor product of these three maps to T, I get T prime. Yeah? And this action here is essentially in the obvious way, right? So if you have F1 tensor, F2 tensor, F3, this acts on decomposable elements U1, U2, U3 in the obvious way. So F1 acts on U1 and F2 is applied to U2 and F3 is applied to U3. Right? So this is the way how this restriction is applied. And then it's very easy to see if and this is an action essentially of the triple endomorphism space. And then it's very easy to see that if T prime is a restriction of T, then the rank of T prime is bounded by the rank of T. Yeah? Because essentially this will turn automatically a decomposition into rank 1 tensors of T into a decomposition of T prime. And even much nicer, they are in some sense also complete tensors. Yeah? So the rank of T is bounded by R if T is a restriction of this diagonal tensor. And this is essentially a three-dimensional identity matrix. Essentially looks like this. It has dimension R by R by R. And then there are ones somehow on the main diagonal. Yeah? Or if you want to write it in some basis, it's just this thing here. Okay, and but we want to work with border ranks, and then therefore we, instead of looking at these restrictions, we will also look at what is called a degeneration. And a tensor T is called so tensor T has border rank bounded by R. Yeah? If it lies in the closure, yeah? Now we can either take the Zariski closure or the Euclidean closure over C, or you can also, if it lies in the closure of all tensors which have rank bounded by R. And in particular, and this is equivalent because this has a complete element. It's essentially equivalent that you are in the orbit closure of this element here of the unit tensor of size R by R by R. Yeah. And more finally, we can also define a degeneration. We say that T prime is the degeneration of T. Yeah? If T lies in the closure of all tensors which I can restrict from T. And then if T prime is the degeneration of T, then the border rank of T prime is bounded by the border rank of T. And if the border rank of T is bounded by R, this is if and only if T is a degeneration of R, the unit tensor. Okay, and now we can briefly explain how Strassen made progress with using this laser method. If you look at this tensor here, we will always view this as a block tensor. Yeah? So we'll cut this into 4 pieces in this particular case. Yeah? So we'll cut it along these dotted lines or dotted planes into 4 pieces. And then it has inner tensors. It has here, this is the 0 tensor, and this is the 0 tensor, but it has these 2 slices here, and these are identity matrices, and these are correspond to matrix multiplication, say, of these 2 kinds here. And I also want to have an outer structure, and the outer structure I get by taking, by shrinking everything here to size 1 by 1 by 1. So it would look like this. So this is now a matrix, which, and I put a 1 in every position, yeah, where I have a non-zero tensor here, right? So there would be a 1 here, corresponding to this tensor here, and there's a 1 here, corresponding to that tensor. And this is again now an identity matrix. And this corresponds to the one-to-one matrix multiplication tensor. And then essentially now you symmetrize everything, and then you get inner tensors. So all these tensors here, they're multiplied in some weird way. Yeah, but they are all matrix multiplication tensors of this particular size here. But the x, y, and z, they can differ, but the product always has this size here. And the outer tensor this is just again a matrix multiplication tensor. So you have an outer structure, which is a matrix multiplication tensor. The inner structures, they are also matrix multiplication tensors, but they don't match, unfortunately. Yeah. And then what Strassen essentially could show is that out of a matrix multiplication tensor, you can get back a unit tensor which has almost optimal size. Yeah? So it's the best that you could get. This lives in this space here. Yeah? So the best that you could hope for as a unit tensor getting out of this would be one of length n squared, but you can get almost n squared. You can get this by degeneration. This is a special kind of degeneration, which is called a monomial degeneration. And essentially all the entries in this transformation matrices, if you view them as polynomials in epsilon, they are monomials. And if you now do this, you have this outer tensor, and you get this diagonal out of this. And because this is now a monomial degeneration, this will somehow don't mess up with the inner structure. And therefore, you get essentially 2 to the 2s, which is simply 2s squared, which is this thing here. Independent matrix products of this size here, and this is the size of the inner products. Yeah. So essentially, Strassen found a way by looking at the inner and the outer structure, by getting a diagonal out of this outer structure, he was essentially able to get a large number of independent matrix products. And this is the situation of the tau theorem. And therefore, he could now prove that omega equals 2.48. It is bounded by 2.48. By essentially now throwing the tau theorem to it. And then the story, this concept that Strassen invented here, this is called subrank or subborder rank. And the rank essentially is always asked, how much do I have to pay to get a tensor? And in some sense, the subrank asks, what can I get back essentially when I'm selling my tensor? Yeah? So this is also sometimes called the cost of the tensor. This is called the value of the tensor. And Q of t is obviously a lower bound for R of t. Yeah? And you can also look at the asymptotic versions. Yeah? So, so far, what you always do, you take a high tensor power, and therefore, essentially, you are just interested of these asymptotic costs. Yes, so it could be the case that a high tensor power is much cheaper than the tensor itself, right? So there are tensors of this example, for instance, the 2 by 2 by 2 tensor, the rank, and also the border rank. This is 2 by 2 by 2, but the rank of this thing here, this is much smaller, because otherwise we could not multiply matrices faster than Strassen's algorithm. So there are examples of tensors where this quantity here gets smaller and smaller and smaller. And this is called the asymptotic rank. And what we really want to bound is the asymptotic rank. This would be sufficient for everything, but essentially we don't know how to do this, at least not directly, because it's already hard to come up with the upper bounds for the small tensors. But if you take a large tensor, this will be very hard to come up with an upper bound. In the same way, you can define the asymptotic subrank. And the nice thing is essentially that the asymptotic rank even lower bounds the border rank. So you don't gain anything by approximation. This is essentially immune to approximations. This will subsume it automatically. And for the subrank, it's exactly the other way around. The asymptotic subrank is an upper bound for the other two quantities. And then Coppersmith and Winograd, they played essentially the same game as Strassen. I don't want to go into the details too much. The tensor is more complicated. There's now a third layer glued to the bottom. And this makes the situation a little bit more difficult because the outer structure is not a matrix multiplication anymore, but it's this tensor here, which we saw in the beginning of polynomial multiplication modulo x squared. And so the contribution by Coppersmith and Winograd was essentially to give a general method how one can degenerate a large diagonal out of an arbitrary tensor. And they essentially applied this, and they got a 2.41. And they also applied it to the second power of this Coppersmith and Winograd tensor. They could get an improvement, and then Yeah, Strassen, Wasilewska-Williams, Legal, and Ellman and Wasilewska-Williams. They all found twists, and you looked at higher tensor powers and got upper bounds, which is something like 2.37, and then there are some numbers following. This is the best we currently know. Now, of course, you can think of can we improve this, but you can also think about maybe you can't do better, right? So what's the answer? And this is what now barrier results are about. Yeah, so what is a barrier result? Yeah, so here's the general recipe how we found our matrix multiplication tensors, the fast one. So we started with some base tensor. Yeah, so for instance, Strassen, he started with 2 by 2 by 2. And then we raise it to a high tensor power. And then Strassen got 2 to the s times 2 to the s times 2 to the s. Yeah. And then we construct a restriction such that we get our matrix product out of this high power. Yeah? And for Strassen, this was easy, right? Because it's already a matrix multiplication tensor. So he just has maybe to zero out some variables here to shrink down to capital N. And what we get by this is then that essentially the omega, the exponent, is bounded by the asymptotic rank of this thing here, of t. But unfortunately, we don't know how to bound this, so we typically bound this by s times the logarithm of the border rank, for instance. And we have to divide it by the size, the logarithm of the size of this of the matrix product that we get out of it. Yeah. And of course, what we typically want, if you look at, we want to have a good upper bound on omega. Yeah, so this should be large. So n should be large. And then it's typically exponential in s, so this s here will go away. This s will go away. It's now hidden here in the notation. So the size should be as large as possible, and of course this border rank here should be as small as possible, because we want to have an upper bound. Yeah, and the barrier result now shows you a lower bound. Unfortunately, not on omega, but it shows you on the lower bound on the best upper bound that you can obtain if you start with a certain kind of restriction and a certain tensor. Yeah, so here we have, essentially we can start with, this is the choice that we can make. We can choose the tensor, and we can choose somehow this restriction here. These are our design parameters in the design of fast algorithms. And yeah, and of course there are now 3 parameters, namely the class of starting tensors, and this should be as general as possible, to have a meaningful result. The type of restrictions that we can use, they should also be as general as possible, because for tensor rank we use general arbitrary restrictions. And of course we want to have a lower bound on the best upper bound that we can obtain from omega, and this should be as large as possible. But it's of course contradicting principles. If you allow for more tensors, you should expect that the lower bound on omega that you will get is smaller, just by, at least it cannot be larger. And therefore, these 3 parameters here somehow, when you optimize for one, it will typically worsen the other 2. And such barrier results, they have already been known in the 80s. So this is right after Schönhage proved his tau theorem. And what they proved is that you cannot prove that omega equals 2 if you just, as our restriction, we do one application of the tau theorem, or you also call it asymptotic sum inequality. And I only have written it as some upper bound, but you also get a restriction out of it. So you cannot prove this with one application of such a restriction to a sum of matrix multiplication tensors. So when you just do this, you start with a fixed matrix multiplication, sum of matrix multiplication tensors, you apply the tau theorem, you will never be able to prove omega equals 2. That was one of the first barrier results. Then there was a result by Ambinis et al., who just looked at the Coppersmith and Vinogard tensor, and only on the method, this laser method, which is used by Coppersmith and Vinogard and Wasilewska-Williams and Stodders and Legal and Ellman and Wasilewska-Williams. So this is a rather restricted setting, but I got a very good lower bound. I think something later larger than 2.3. So if you, with this massaging of the Coppersmith-Vinogard tensor, you can't expect that you get much better results. That's what I proved. And then Ellman and Wasilewska-Williams, they looked at monomial restrictions and generalizations of Coppersmith and Winokur tensors, and they could prove some lower bounds. Yeah? And then maybe the most general setting, but of course you get the worst lower bounds in omega, is was by Castandel et al. And then they took arbitrary restrictions and they looked at what is called an irreversible tensor. And I will define what an irreversible tensor is in a minute. Yeah. And so this is what we want to use, and what we now want to look at. We want to look at tensors of minimal border rank. So here's the roadmap of our results. As I said before, to get this upper bound in omega, this should be small. And whenever you have a tensor T, which is concise, which means that you can't shrink the slice, there are no dependencies between the slices, which is something natural. Then this format of the tensor is a lower bound for the border rank. And the best you can hope for is that equality holds here. Yeah? And this is what we call a tensor of minimal border rank. And for instance, the Strassen tensor, which he uses in the laser method, and also the big Coppersmith and Winokur tensor, which I didn't show you, but which is used for the better upper bound of 2.37, they all have minimal border rank. Yeah? So this is exactly the setting where we are in. Yeah? And this is, of course, these tensors, they are characterized, but they're characterized in complexity. So the border rank should match the dimension. Yeah? And the first thing that we could do is we could give an algebraic characterization of these tensors. Yeah, so what we essentially could prove, maybe slightly more, a little bit of notation. So the theory of tensor degenerations by Strassen, this is essentially inspired by this concept of deformation theory of algebras, where there's one fundamental difference. Namely, in our setting, we have the triple GLN acting. Right? So there's GLN V tensor GLN V tensor GLN V, for instance, acting. And in this deformation theory of algebra, we only typically have one GLN acting, and it will act in the same way. Now I have written it here for bilinear form, so ignore the duals and maybe the inverses here. So it will act. It will act in this way, yeah, and it will act on the two inputs, and it will also act on the output. Yeah. And whenever we have this kind of degeneration, we call it an algebraic degeneration. And of course, when you have an algebraic degeneration between bilinear maps, this is an arbitrary degeneration. And the funny thing is that whenever you have two bilinear maps, yeah, and one of them is a degeneration of the other in the tensor sense, yeah, it is always a degeneration in the algebra sense. Yeah, so a tensor degeneration, which has, but you have to use this particular form here. Yeah? So this applies an algebraic degeneration. And algebras, which you can degenerate out with algebraic degenerations out of k to the n. So this is a commutative algebra with pointwise additional multiplication. They are called smoothable. And so what we essentially now have proved here, when you ever have now a special bilinear map, which are called unital, that means there's an identity element in this bilinear map. Yeah? In particular, the multiplication map of an algebra is always unital. And for unital bilinear maps, now tensor degeneration and algebra degeneration, they are the same. And this means that a unital bilinear map of this corresponding tensor here has minimal border rank, if and only if it's a multiplication in a smoothable algebra. Yeah? And this essentially gives you, here we have minimal border rank. This is a complexity theoretic definition. And this is an algebraic definition. Yeah? And so therefore we essentially know, now unfortunately this concept, the smoothable algebras, they're not completely understood, but this would give us a way an algebraic way to understand these tensors of minimal border rank. And of course, one can hope for, you can look at all the smoothable algebras and see what you get out of matrix multiplication. Out of this, we tried it, and also the group around Mateusz and Michalek tried it, but unfortunately, we couldn't get any better upper bound on this. So there are some examples. So there are some algebras which are known to be smoothable. And for this, you can try to get fast matrix multiplication algorithms. You can also look at the starting tensors used in fast matrix multiplication algorithms. And now you know if they have minimal border rank, they are also smoothable algebras. Yeah? So it goes in both ways. So unfortunately, we couldn't get any better upper bound on omega for this. Yeah. And now we can use this characterization to essentially get some characterization, some Berry result for tensors of minimal border rank. And for this, we need to define the irreversibility of a tensor. Yeah? This is just this quotient here. So you take the asymptotic rank, and you take the asymptotic subrank. And you take the logarithm just for normalization purposes, and you would divide these two quantities. Yeah? And this was always a lower bound for this. Yeah? And if these two things equal, yeah, then this tensor is called reversible, and otherwise it's called irreversible. Yeah? And what Kristandl proved that when you have an arbitrary restriction from powers of some tensor, it's impossible to prove an upper bound of omega that's better than 2 times the irreversibility number. Or to put it in the other way, if you start with an irreversible tensor, you can never prove that omega equals 2. And this is due to the fact because this subrank for matrix multiplication, this is maximal. And this thing here is equals the subrank exactly when omega equals 2. This is essentially the whole. So once you have made a definition right, so this theorem is very, very easy to prove. Yeah? But this means, so for our purposes, if we have a tensor and we start with it, and this number here is not 1, then you will never be able to prove omega equals 2, no matter what restrictions you use. Yeah? And this is what we now want to use and apply it to tensors of minimal border rank. And essentially what you simply have to prove is that tensors of minimal border rank, they are irreversible. That's what we have to prove. Unfortunately, it's very hard to get hold on this quantity, yeah? But we can bound this quantity by what is called the asymptotic slice rank. Yeah? And if the asymptotic slice rank is not maximal, then it turns out that the tensor T is irreversible. Yeah? In particular, and if this is not maximal, if and only if the tensor is unstable in the sense of geometric invariance theory. Yeah. And what we then prove is that the structural tensors of algebras with radical, they are unstable. And in particular, the structural tensors, the smoothable algebras, they all have a radical except for the trivial algebra. And therefore, all these starting tensors of minimal border rank by our previous characterization result, they will all be irreversible, and therefore you can never prove omega equals 2 if you start with them. That's essentially the whole idea. And what is slice rank? Maybe just briefly introduce it. So in the case of rank, you start with these kind of tensors. And in the case of slice rank, essentially you're allowed to take, you start not with, you don't have 3 times, but you have always a vector together with a matrix, or a matrix together with a vector. Or you have the third form where you have to cut a matrix into 2 halves, so I cannot write this down here properly. Yeah. And then the slice rank is essentially the smallest number R, such that now we have simply other basic building objects that you can write T as the sum of these building objects. And the slice rank is sandwiched between subrank and rank. And then the asymptotic slice rank is defined like the other asymptotic ranks here. Yeah. And now a tensor is called unstable, is 0 contained in the Zariski closure under the SL action, triple SL action. And they form a cone, and this is called the null cone. And there's a theorem by Burgers et al. That the tensor T is unstable if and only if the asymptotic slice rank is not maximal. It can never be larger than n. And if it's not maximal, then the tensor is unstable. And now essentially, just let me briefly go over this. What we now can prove that whenever we have a tensor of an algebra with radical, then we can essentially prove that they are unstable by essentially giving some appropriate weightings to the parts of the tensor, and this allows us to to find a one-parameter subgroup which essentially drives the whole tensor to zero. That's the overall idea. The details are a little bit tedious, but that's the way how we achieve this. Yeah. And then essentially, and you can also get quantitative versions out of it. Yeah, so you can even prove a lower bound on the irreversibility number in terms of some structural parameters of the algebra. Yeah, but the actual formula, it's not so illuminating. It simply comes out of corresponding bounds which you can get out of the moment polytope. Yeah. But what you get from this is essentially that it's impossible to prove omega equals 2 when you start with a structure tensor of a non-semi-simple algebra which has bounded dimension. Yeah, the only way to achieve omega equals 2 you would have to have a sequence of algebras that I cannot rule out, which gets larger and larger and larger, and it gets better and better and better bounds on omega. But when you start with one fixed dimension, this will not work. Yeah? And because the tensors of minimal border rank, they have this characterization in terms of smoothable algebras, then what we can show is that whenever you have a tensor of minimal border rank, which has not minimal rank, so it's not which essentially is just it's not this algebra here, then it's impossible to prove omega equals 2, yeah, using powers of such a tensor with a fixed dimension. The only thing that we have some structural restriction, but which is not too restricting. Yeah, so whenever we have this tensor, you need that. So what is called 1v1 generic. You want that the number of the slices here. So I can think of this tensor here as the slices, and then the one slices. So when you take these here as matrices, they need to have an element of full rank. This is what we call one generic, and we also need this something is two generic here. And this is only true for tensors of minimal rank, which are one generic and two generic, because to them this structural result applies. This has also recently been relaxed by, unfortunately, by some Polish guys. I forgot the name, but if you can look it up, you can even drop this thing here. So it's even just no, it's called the binding definition is the same. But you don't need this two genericity. You only need this one genericity. And this is essentially achieved by generalizing our structural result for algebras to essentially modules. Good. And so maybe let me stop here. So the takeaway message is essentially if you start with a tensor of minimal border rank, you essentially will never be able to prove omega equals 2, right? So you have to come up with something more clever, and I have no clue what this could be. Okay, so that's it, and thank you very much.